It's time for your favorite class. Oh, no, I'm sorry. It's wrong class. It's time for 126. Here we go. So we are going to recap a little bit of 1D interference. There's a few things I said that I didn't quite completely say last time, I think. And also, the week one homework really just had two 1D interference problems, and one of them was really hard. It didn't have any good warm-up foundational building interference problems. So I'll work a little bit of 1D interference onto this week's homework that'll be out later today. Okay? And then week two, we have goals there or skills there on the website. I didn't quite make it to the printer. We'll have this printed Thursday, but we're going to do a little bit more 1D, and then we'll go straight into calculating phase differences for 2D. It's not twice as hard. It's not linear. Okay, so 2D is pretty much the same as 1D. So we'll deal with 2D stuff, and then we'll talk about beat frequencies today. And then Thursday we'll get to light. All right, that's basically the plan. I had this problem up before class if you wanted to look at it, because we're going to do it. We're going to do like this practice problem. So if anybody really wanted to work on it ahead, they could have. But it doesn't matter. We're going to do it all together. Let's turn this off and have a quick reminder about beats, or about 1D. All right. So it's really dark. No, that's all we got. Okay, so 1D interference recap. There's one little place I kind of was freestyling off my notes a little bit, so I wanted to say it one more time. So remember, 1D interference was sort of an application of superposition. The idea that if we have an axis here in the x, and we put a source here. So usually we draw the source as a little speaker box or something, vibrating, sending out a sound wave. So we'll call it sort of S1. You know, it's going to send out a sound wave like this. And say we have source 2, a second one, and maybe a different position. All right? It's also going to send out a sound wave. And then here we have a detector, which I don't know, I keep drawing as a big ear, which I don't know why I keep doing that. Okay, that's the detector. We'll call it, D for a detector. And the question is just, what do you get at D? Do these two overlap in a way that gives you constructive interference? Do they overlap in a way that gives you destructive interference? Do they do something in between? That's what we're trying to figure out. Let's see. The key to figuring it out, is to know the phase difference between these two. And we wrote it all out last time. I'll just sort of remind you this time. We usually call the total phase difference between the two delta phi. No subscripts. Right? That means it's not just for 1, it's not just for 2. It's the difference in all of them. Of course, that's equal to the phase of 2 minus the phase of 1. What I'm going to show you today is that if you have problems where both the phase and the position change, and we're going to do two problems like that, you do need to keep up with which one is first and which one is second when you do the difference. You can do 1 minus 2, 2 minus 1, doesn't really matter, but you do have to keep it straight to get the answer right most of the time. So what is this equal to? This is equal to delta x over lambda 2 pi. That's the displacement different part. That's the difference in the distance. And plus the difference in their phase constants. Right? So we always have a not on there. Find not when we mean the phase constants. Okay? And there's one little subtlety. There are mathematically lots of ways you could go on what delta x means. All right? Does delta x mean the absolute position of the speakers? Does it mean the relative position of the speakers? What does it mean? So it could mean anything, and the math will work out if you write the equations right. Let's go with what the book says. Let's do it exactly how the book says it. And we're going to say that delta x is the difference. It's got to be a difference because it's a delta. But they define it as source to detector distance. That is what x means. x1 is the distance between source 1 and the detector. x2 is the distance between source 2 and the detector. They're not the position on an axis in this case, how we're defining it. Okay? So if I were going to draw x1, I would say it's that, and x2 is that. Okay? You can define it different ways. You just have to be consistent if you want to get an answer that makes sense. So we're going with what the book said. That's what the book said. What else? And phi naught is just the difference in phase constant between 2 minus 1. So you know what that would be. I think that's all I want to say about that. So then the part that I shortchanged you a little bit on is the definitions. When is it constructive? When do you get constructive interference? I said, oh, well, when the difference in phase is 0. If the two waves are in phase, the difference will be 0. But there's more than that. It's really 2 pi times m, where m, in this case, equals 0, 1, 2, 3, etc. Basically all the integers. Okay? That's not the same m as in standing waves. Right? We always use m when we're talking about a bunch of integers. So it's the same idea. We're using different integers, but it's not like you can't take that m and plug it into a standing wave problem. That's not exactly the same thing. All right? So the only thing I think before is I was just going fast or got out of my notes and said, oh, this is when it's equal to 0. So it is 0, but it's also basically any difference of 2 pi, because 2 pi is a whole wave. Right? So if you have two waves constructive interfering, perfectly overlapped, and you moved one by a wavelength, they would still be constructively interfering and overlapped. Right? And if you moved them by 2 wavelengths, they would still be overlapped. Right? So that's why you can have multiple values. Destructive, same story. Destructive, when delta phi is also 2 pi, and we'll say m plus a half. Where m, same value, 0, 1, 2, 3, blah, blah. Right, so if the difference in phase is m equals 0 is a half of 2 pi is pi. So if two waves are pi out of phase, that means half a wave out of phase, you'll get destructive. So again, I think I just said 0 and pi, I think, is what I said last time. I don't know how much we're going to do it, but I do want to at least write it down so you know it. It'll probably show up on the homework somewhere. In between. Can the waves be in between constructive and destructive? Yes, sure. It doesn't have to always be exactly one or exactly the other. You can do a bunch of math and trig identities, blah, 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 to show that then basically you get a sinusoid at a reduced or at an amplitude in between. Somewhere between this one, you remember, comes out at twice the amplitude, if they have the same amplitude. This one comes out at 0. This one comes out in between, where it's basically amplitude of the wave is really all we calculate. And it's 2 times the amplitude. This is what you would get if you had constructive interference, times the cosine of the delta phi over 2. Right? So if you calculate this, and let's just for funs say, oh, what if we put in 0? Cosine of 0 is 1. Hey, we get constructive interference. Look at that. What if we put in pi? What's cosine of pi over 2? 0. We get destructive interference. This is what you get in between. Cosine of the phase difference over 2. It's called the power factor. Don't ask me why, because I will tell you, and it'll take 15 minutes. Good. Okay, good. You don't want to know. Good. Because I don't want to tell you. It's a long story. But it's called the power factor. I just like to say that. All right. Okay, so that is your review, or that's sort of a recap and sort of a filling in the gaps of pretty much all you need to know about 1D interference. So all you need to know now is how to use it. Okay? So that's why we're going to now work a problem here. This one. Going to work this problem in painstaking detail. Oh my God, it's going to be, is 2A the max amplitude? Yeah. So what I didn't say here, but implying that each wave has an amplitude of A. Right? This has A and this has A. So if you constructively interfere, it'd be 2A. Yeah. We'll talk more about how amplitudes can be weird later. Okay? Here's our problem. So if you were facing a problem like this, let's think about what would you need to do? Oh, the lights aren't on. This is a tricky one, I would say, because it varies both the position and the phase. It's not one of these quickie, well, assume delta phi phase is 0. It actually, we have to think about varying both the phase constant and the position. All right? So let's look at it. First thing I would do is kind of draw it. Right? Let's look. Well, no, actually, the first question I forgot is this. quick thing. Two speakers, same position along an x-axis, make beautiful music at 240 hertz by a detector a few meters away. Okay? So that's like what just when I had the two speakers and we put them in phase and out of phase, in phase, out of phase. When we had them in phase, it was loud. So that's what you have going. But now instead of when I switch the wire to make it out of phase, imagine it just for some reason, one of them jumped by 247 degrees. Right? So that's more than 180 degrees. Right? So but it's not quite 360. So it's somewhere between these two cases. You would have to do this to get the amplitude. Right? So it jumped by 247. So one question is, how are you going to get them back into phase? Okay? So first, let's draw this before the shift. And then I think we'll be able to answer the question. So before the shift, we had, let's say this is like the origin, and here's one of the speakers. Okay? And it's making, let's say it's a sinusoid. Okay? So it's like this, a nice sinusoid. And then here's the detector. Beautiful music. All right. And let's see. Yeah. And now, what about the other detector? I like to always label them 1 and 2. All right. So there's detector 1. I'm sorry, source 1 and source 2. Here is source 2. All right. And at the beginning, they're in phase. They must both be making a beautiful sinusoid. Right? This part will be here. This part will be here. I'm going to try to draw it the same, like that, like that. Beautiful sinusoids in phase. If I had to write this as a function of x, I would just say, oh, it's just sine x. I mean, it's really kx. Okay, let's write it as sine kx. And this one also, sine kx. Right? Everything's in phase. Beautiful. I love it. I kiss it. Okay. What about x1 and x2? I could draw x1 and x2 on here. It's the distance to the detector. There's x1, and there's x2. Beautiful. Now, let's read the story here. Suddenly one of the speakers shifts by minus 247. Let's try to draw that. After the shift. All right, looks like this. So, one of them shifts. Let's make number 2 shift. Which means we're going to draw number 1 exactly the same. Nothing happened to number 1. Okay? So there's number 1. It's still sine kx. Okay? There's still an x-axis. The detector's still over here. And it's still making a sine. Well, everything's the same. Let me just draw it exactly the same. All right, it goes through a cycle and a half. Okay? Now, let's draw the other one. It didn't move. It just had a phase shift. Like whatever electronic source is driving this wave just changed by negative 247 degrees. Okay? So I would write that. First of all, I'd write it here and say, well, it must be sine kx minus 247 degrees. You say 247. I'm going to put 247 degrees because I don't have a lot of room. And you can just deal with the fact that this is in radians and this is degrees. Obviously, when we do the equations, we'll convert everything to radians. But you get the idea. This shifted by about 3/4 of a wave. Right? 270 is 3/4 of a wave, so a little less than 3/4 of a wave. And I told you the phase shift is negative, which means you add kx plus negative 247. But to really get into this problem, you've got to know which way is that sinusoid going to move when it's negative in the phase. It moves to the right. Kind of like we talked about why a wave would move to the right. So what that means is this point right here is going to move forward 247 degrees. 247 degrees is about there, right? Almost to 270, somewhere about here. So let's draw a little dotted line right there. And all we got to do is just start this wave now here, right? So it's going forward a little bit. So it's going to come up like this. And I want to make it end at the right place. This one made it down to here. So we have not quite a full sinusoid here. So it's going to go kind of like that. Right? This one made it back down to 0. The width of this thing is 1.5 cycles. This didn't quite make it because it started where it didn't quite make it right there. So that's what sine 240, or kx minus 247 would look like if you're going to draw it. Shifted it to the right. And we could say, well, it's continuously going all the time. We could actually go ahead and fill in this part. Right? It must be kind of like that. So that's really what it would look like there. I just drew it in. Look at this, beautiful. Okay. So then you look at it, and now, why isn't it sine kx plus 247? Because I put a negative sign right there. So I said it shifted by minus 247, so that's what you stick in the equation. Once you've stuck in the negative, you know that that moves it to the right for reasons you can figure out on MATLAB or your calculator. Or we could go through it again in my office. So now we could probably maybe answer part A. You can get them back in phase by moving which one? What are you going to move? You could move, if you want to get them back in phase, what could you do? You could pull this one back, maybe pull it back to where this is happening here. Seems promising. You could move both speakers forward, right? Maybe. You can move both speakers backwards, or you can move the detector. So which one of these is going to get it back in phase? Let's do our audience response, verbal audience response. I'll count to 3 and say your letter. 1, 2, 3, A. Yes. Only A will change the relative phase between these two. Moving them both won't change the relative phase. Moving the detector won't change the relative phase. Only that. All that setup was just for that. Oh, man. No, not really. Now we're going to do more. Going to keep going. All right. So, smarty pants, if you must move it to make this work, how much do you have to move it? So you can think about that, how you would even start approaching that while I erase the first board. We'll see how we do on that. You can maybe do it quick if you think you know how to do these problems. I'm going to do it in painstaking detail. Let's see. Couldn't you move them both backwards but by different amounts? Yes. It was implied when you move them both that you move them together. Okay, I'm running out of room. Oh my God. A mess. Let's see. Yeah, you move them together. Let's see. Okay, how far back do you have to move the speakers? Blah, blah, blah. Okay, here we go. Let's see. So to figure that out, actually, one more thing I meant to write up here is to get started, I need the room on this board, so let me pull this one down real quick. To get started, you might do a couple things. You got to decide, okay, we're going to move one of them. Let's decide which one you're going to move, first of all. I think actually I made you to make it all get the same answer, right? How far back do you have to move the phase-shifted speaker? Okay, so one thing to note before we get going is you're moving X2, the phase-shifted one. And then the other thing, one quick number we can get right away, is the wavelength. Right? We're going to need the wavelength, and you know the frequency. So there you go. Let's see. So get lambda from V and F. So hopefully you would click immediately and say, oh yeah, 343 meters per second is the frequency, which was 240 hertz. 240 hertz times lambda. Okay? So lambda, in this problem, it's 1.43 meters. Right? So that's a quick calculation. You would need the value of lambda. And it was given to you because you have that and because this is sound. Someone's asking, do you add or subtract 247 degrees? That's the whole point of me doing it in painstaking detail. So I'll show you. You subtract it, and when I just wrote the equation, I said it's negative, so you put it in negative. But I think you mean in the delta phase part that we're about to do. So you make it positive or negative. That's the entire idea. That is what we're going to figure out. So hold on to your hats. Hold on to your hat. Here we go. Got one hat. Just one. That's weird. Okay. Okay. So to solve any problem like this, you use the phase condition. All right? And you know what it is. We want it to be constructive, so we're going to say delta x over lambda times 2 pi plus the difference in the phase constant equals 1. We got to decide what signs to put in for everything. Also, what are we going to put here? 0, 2 pi, 4 pi, 6 pi, 8 pi, 10 pi, 12 pi, 14 pi, 16 pi, 18 pi, 20 pi, 22 pi, 24 pi. Let's go with 0 to get started. Oh, yes. Okay. I'm not ignoring questions. It's the same one. I don't know how to make my phone only tell me once. Okay, so this is constructive, right? Because we have an integer multiple of 2 pi. Okay, so here's what you got to realize is since both delta x and delta phi change, keep them straight. Okay, that's not a mathematical statement. I'm just saying you do have to pay attention to the signs, just like the person's asking, is it minus 247 or plus 247? So what I would do is keep your numbers in mind. We have 1 and 2. I would say let's make delta x x2 minus x1. Right? And that doesn't mean their position. That means how far away they are from the source to the detector. Right? And let's say delta phi that we're going to use must be phi 2 minus phi 1. Those have to be the same. It's got to be 2 minus 1, or it's got to be 1 minus 2. You can't mix it up. Okay? So let's plug it in. Without worrying about negatives, let's just plug it in and see what we get. Delta x, oh my God, which is it? Oh, that's what we're looking for. Good. Delta x. We don't even know delta x. Over the wavelength, we just figured that out. 2 pi. 2 pi. Plus, and now here it is. Minus 247 or plus 247? Well, let's see. It is subtle. Phi 2 minus phi 1. What is phi 2? Well, really, it's the phase constant. It's the whole phase constant. It's not even just 247. It's whatever we had, phi naught 2 minus 247. And up there would be phi naught 1. But we know that originally phi naught 1 equaled phi naught 2. We just called them 0. Basically, when I wrote those two things as signs, I said the phase constants are 0. Because I called it a sign, and I made it start and look like a sign. So the phase constants were 0. So really, we could then just say the phase constant of 1 is 0, and the phase constant of 2 is minus 247. So that's why we say minus 247 minus 0. Right? That's phi 2, and that's phi 1. So the answer is you put in negative 247. If I were doing 1 minus 2, I would put in plus 247. Because it would be 0 minus negative 247. Right? So it totally matters if you're doing 1 minus 2, 2 minus 1. So there you go. And if you want to convert degrees, then you say how many fractions of 360 times 2 pi. So there, I just converted degrees to radians. Thank you. And that's going to be equal to 0. We decided to set that equal to 0. So that is the super explicit way to set it up. Right? Both differences have to be 2 minus 1. You really think about what is the phase constant, and then you solve for delta x. 2 pi's go away. So you get delta x over 1.43 equals 247 over 360. All right, the 2 pi's went away. And you get delta x is 0.98 meters. Right, and that is correct. But what does that mean? Delta x is 0.98 meters. Is that a position? What is that? We got to think about what x is. What does that really mean? Delta x is positive. And what did we say x was? X is the difference in the distance to the thingy, right? It's not the position on the x-axis. It's the distance between the source and the x-axis. Oh, how did you get 1.43 while you were sleeping? I got it right there. 343 divided by 240. That was a movie, While You Were Sleeping. Sandra Bullock, subway token taker, very realistic. Okay. Why does the equation equal 0? Because we set it equal to 0 because that's our condition for constructive phase, constructive interference. In a minute, we'll set it equal to 2 pi. 2 pi. Okay, so we're talking about why delta. What does that mean? If delta x is positive, what does that mean? That means x2 is greater than x1. Because right here we said it's x2 minus x1. x2 is greater than x1, so what does that mean? How do we move it? If x2 is greater than x1 and it's equal to 0.98 meters, have we moved it forwards or backwards? I know because I wrote it down here. We moved it backwards. We predicted that you move 2 back. Right? x2 greater than x1, they were like this. They're still like this when we shifted the phase, but to get them in phase, we solved for the case where you drag this back by a meter. And sure enough, it makes sense if you look up here, right? If this is 1.43 and we went a little bit less than 3/4, that would be about a meter right there, right? So if you drag this back by a meter, you'll be back in phase. So it seems to work because I kept every little detail straight, right? How far backward do you have to move the phase? And backwards. We could have screwed it up and done forwards, and I just knew ahead of time which one to do. I actually just did all of them and used the right one. It's hard to know ahead of time. We answer a few questions, and then we're going to do more. We're going to keep going, okay? Could you solve this using proportion of phase difference in the wavelength? That is what we did. Right? The proportion of phase difference is right there, and the wavelength is right here. So yes, you can solve these intuitively in 8 seconds if you want. I'm just showing you every little detail, because sometimes when you have phase and position changing, you got to use these details to really get all the signs to work out. Okay? Let me show you what I mean. So backwards, forwards is referring to how to get back in phase. Yes, yeah. How far backwards do you have to move the phase-shifted speaker? So we just solved it. Okay, let's move on, or I'll just ramble about this for like a long time. How far forward do you have to move it? So we did all the math and we got backwards. How are we going to get forward? All right, what about forward? Okay, so what we're going to do now is get rid of this and give me another board. So same problem as just forward. All right. Never mind. Okay. Oh, the lights are, okay, yeah. Okay. How do you get forward? Right, so that makes no sense unless you understand it's a continuation of this problem, okay? You could say, well, maybe forward is to use another value here. What if we use 2 pi there? Let's plug it in and see what happens. We won't spend much time. Delta x, oh my, well, we'll at least write neatly, over 1.43 meters times 2 pi plus, phase is the same, minus 247 minus 0 over 360 times 2 pi equals, so instead of 0, let's put 2 pi. Right. That's another case of constructive interference. Also, constructive. All right, spin it around, blah, blah, blah. This is 1. And basically, you get delta x over 1.43. Instead of whatever 247 over 360 is, it's 1 plus 247 over 360. Right? 247 over 360 comes to this side plus 1. There. What's that going to do? It's going to make the number bigger. It's going to give you delta x equals 2.41 meters. Positive. If it's positive, that means push it back. Before we pushed it back 0.98 meters. Now we're pushing it back 2.41 meters. So we didn't push it forward, did we? We pushed it further back. Okay. So in this case, going to higher m here, 4 pi would push it further back. 6 pi would push it further back. 8 pi would push it further back. That's hard to say. How far further did we push it back? What's the difference between 2.41 and 0.98? 1.43, a wavelength. We pushed it back by a wavelength. Of course, that's what happens. When you have 2 signs overlap and you have a constructive case, if you move by a wavelength, it's constructive again. So it makes sense that the difference in these is yet just another wavelength. Okay? I mean, 1 times 1.43 if you're into algebra. There you go. It shows up every time. Okay. Well, how do we get it to go forward then? Right? If we want it to go forward, we need this thing to come out negative. Okay? Let's see. We need it to go the other way. Well, there's a sneaky way to do it. The sneaky way, well, let's see, if we were at 0.98 and we went by a wavelength to get to 2.41, what would the sneaky way be? Just subtract a wavelength, right? Negative 0.45. That's the answer. We're done. Good night, right? It's going to be a wavelength the other way. And since that number comes out negative, that must be the case where the thing moved forward. Because that's a case where x2 minus x1 is negative, which means x1 is smaller than x2, which means we must have pushed it forward. Oh, but do you have to be that smart? No, I would not be in physics if you had to be that smart. Okay, let's do it with the equations. We would say, what are we going to put? Delta x over 1.43 times 2 pi plus minus 247 over 360 times 2 pi. What are we going to put here? Negative 2 pi. What's the author's name? I forgot. The book is by Knight. Knight doesn't think you can handle the concept of a negative number there. He thinks it'll blow your young little minds, so he doesn't trust you with this information. Okay, but you are smart enough to know it's not just 0, 2 pi, 4 pi, 6 pi. It's also negative 2 pi, negative 4 pi, negative 6 pi, negative 8 pi. That just represents moving the waves the other way and finding regions of constructive interference. Okay? So if you do this, trust me, you'll get delta x equals negative 0.45. So sometimes you got to put in a negative. The problems we write, who knows? I'm not predicting anymore. Okay, you might need a negative, you know. The easier versions of these problems often have one of these 0, right? It's fixed, and you just solve this, or this is fixed, and you just solve that. And one of them is 0, and they're pretty straightforward, and you can't screw it up. But we like to do ones where they both change, because that really proves you really know what's going on. All right? So there's like half a lecture on a practice problem. Okay. Cool. What time is it actually? Let's see. It is actually 9:57. I can do all of 2D interference in 3 minutes, believe it or not. It's that stupid. It's one drawing. Let's do it over there. Let's get the pretty picture over here. It's like literally one drawing and a GIF is all it is. Like a legitimate GIF, not a funny GIF. Let's just be real. Let's look at a two-dimensional wave. Right, a two-dimensional wave is a point source that spreads into a growing circle. That's my simple definition. That's not a very good one. All right, so it looks like this. Here's your source now. Ooh, S for source. And you draw circles around it like this. And if the circles are good, people say, ooh, he's good at circles. If the circles are bad, they say, oh, he just cares about research. Let's see. All right, there we go. Look at those circles. I love my research. Okay. So when you draw it like this, the circles are the maxima of the sinusoid. Okay? It's really just a way of representing, in 1D, I can draw this sine wave because the y can be the deflection of the sine wave or the pressure or whatever. When I'm drawing 2D, I've got x and y on the board. I don't have the third dimension to draw the amplitude. Right? So we just draw these lines that kind of represent the maxima. Right? So this would be going kind of like this if I could borrow this dimension for a second. May I borrow the y dimension temporarily? Right? It will look like this. Maxima. Maxima, maxima, kind of like that. So that's all that represents. The circle represents where the disturbance is maximized. The wavelength, therefore, is the distance between the circles. And you can see I tried to draw it uniform. There's a lambda, 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 like that. Hey, I'm in a fret. And let's see. Now we've got to write the formula for this. The disturbance, instead of saying xt, we write rt. Because this is like a cylindrical waves or cylindrical coordinates. All we care about is where we are in R. We could go that way, we could go that way, we could go that way. Right? So it looks very similar. A sine kr minus omega t plus phi naught. Okay? What's the same? What's different? Okay? So one, this is the amplitude of the wave. That's the same. Instead of one-dimensional x, it's two-dimensional r. It could be in any direction. This, A, when we first met, I told you that uppercase meant something was constant, and lowercase often means it's not constant. Maybe it was somebody else. There's so many. Basically, the amplitude decays for a two-dimensional wave. I mean, it depends on the type. But a circular one like this, if it has a certain amount of energy, the amplitude actually goes down. So we write a lowercase a. In this class, we're not going to get deeply into how does it decay, probably. Maybe when we get to light, we talk about that. But for now, don't worry about it. It changes a little bit. Same, R is radial position, same. Everything's the same. Okay? So it's really just doing 1D in a bunch of different directions. That's really all it is. All right? And another thing that we're going to do for now in this class is we're going to have no angular dependence. for a real wave, you could imagine that, the speaker sends most of its sound forward and not so much backwards. And the amount of sound you get would have some weird shape. So for now, we're not doing that. We're doing perfectly symmetric, circular waves, things like that. Okay? So that's a circular wave. So after the break, we'll do the interference of the circular waves, which is also very much just like 1D. We have so much to do. Okay, so now I'm going to do 2D interference. You saw how a 2D wave is a lot like a 1D wave. It's just we say it can go in any radial direction, and we just place x with r. So now let's see what would happen if we overlap two of those. All right, so here is source 1, and here is source 2. Hold on, let me get out my Picasso. Wait, no, not Picasso. Okay, somebody that draws well. Like nice geometrical whatevers. So you would draw that like this. Oh, it's hard. You got to start at the top and not think about the overlap. There's no overlap. I don't see it coming. Oh my God. Okay, and you got to start up here. I don't know. God, this is hard. Don't look. All right, like that, and then start here like this. Oh shit. Let's see. Okay, there we go. It looks something like that. Wow. Okay. So you got to ask yourself, where is this constructive interference? Say, well, anywhere these two maxima overlap is constructive interference. It's hard to look at. This one actually did this okay. There. On this line right between them, it's constructive interference. Right? Where is it destructive interference? Or where is it constructive again? Here. Kind of like that. Not bad. Look at that. I botched it there. Maybe it's that one. One's missing there, like that. And in between, look, this is destructive here. There's like no crossing amplitudes there, and destructive there. It kind of sucks. Let me see your notes. Yeah. Okay, so now what we're going to do is look at a computer generation of this. Here's the single wave moving out, right? Wow, look at that. Unbelievable. Let's see. This is actually better. Let's see. There we go. So here is a spherical wave. It's moving up, right? So bright is high amplitude, dark is negative, right? So positive, negative. And here is two on top of each other, or two right next to each other, right? So one is like here, and one is like here. So you end up with something very strong, positive, negative there. Very strong, positive, negative here. And you get some regions where it's just zero. And that's just where they're always in phase and where they're always out of phase. Okay? It's just hard to draw. You don't really have to be able to write the equation for that. Well, it'd be trivial to write the equation for that actually. You just add these two circular waves. But what we really do in these problems is just say there's two sources here, what's happening here? And you can imagine all you're really doing is writing the sum of the two sinusoids with two different distances, R1 and R2. And there's really no reason that R1 and R2 aren't just like X1 and X2. Okay? So 2D interference is basically the same. You just say delta X becomes delta R. Okay? And it's pretty. The other difference is it's pretty. All right? I think it's pretty. So then let's write the phase condition. Delta phi. Here we go. Can we do it? Oh, it was an X. Now it's an R. Okay, I did that all right. What about, does this affect the phase? No. And it's the same. All right, everything's the same. You would say we have two sources here. Source 1, source 2. You don't have to draw all that. You just say, where do I want to have the detector? Detector here. So you say, okay, there's this line, R1. There's this line, R2. Okay, and delta R, you don't worry about 2D. What is delta R? It's really the magnitude of R2. It's just the length. Okay, if you wanted to call them vectors, if you're worried about that, don't worry about that. It's just the length. It's just the distance. This is why it's easier in 1D to not talk about the position along an axis. It's better to talk about distances. That's how we always write these equations in terms of these distances. And then that's all you got to do. Okay, and delta phi naught is the same as it is in 1D. Right? It's the phi naught of 2, the phase constant of 2, minus the phase constant of 1. Or you can do 1 minus 2, whatever you want to do. Let's see. What if there are different wavelengths? Oh, we're going to do that at the end if we have time. That's beats. Let's rush so that we can get there. It's very exciting. The constructive, destructive is the same. I'm not going to write it down. Okay? Constructive is 0, 2 pi, 4 pi, 6 pi, negative 2 pi, negative 4 pi, negative 6 pi. And destructive is pi, 3 pi, 5 pi, 7 pi, negative 3 pi, negative 5 pi. So all that stuff is the same. Okay? So now we're going to make this pattern. You are going to make this pattern. This is the demo everybody is going to participate in. But you don't have to get up, and you don't have to tell me what college you're in. Okay? Not required. I don't have 200. Probably I do. That's right. Okay, so what we're going to do is we're going to listen to 800 hertz. Why is there no sound? Oh, because I pulled the plug here. Okay, so 800 hertz is coming out of these two speakers, and they're spaced, right, a little bit. And oh, God, okay. 800 hertz. There it is coming out of one speaker. I'm going to add the other speaker, and depending on where you are, you're going to hear it go up or you're going to hear it go down. I'm not going to take your picture. I'm just messing around with my camera. Okay. So what I want you to do is close your eyes because you don't want to be biased about where you are. Okay? You're going to close your eyes. And when I add the second one, if you hear it get louder, hold your hand up. If you hear it be the same or softer, don't hold your hand up. Okay? Hold your hand up and don't open your eyes till I say, and then keep your hand up and open your eyes, and we can look around and see if we have bands. Here we go. I'm putting it in. Are you ready? Here it comes. If it thinks it's going to get louder or softer. Raise your hand if it got louder. Shit. Okay, everybody look. Okay. Everybody thinks it got louder. What did I do wrong? Let's see. Yeah. No one. Okay. Let's turn it off. Did anybody hear it get softer? Okay, I calculated a few people. Y'all ears are messed up. Y'all don't know what you're doing. I calculated, and there should have been bands through this thing. Okay. If you watch the video later, that part will be missing somehow. It's like a little edit in there. I'll go, it'll be one of those, right? Okay. Okay, let's do the problem. Okay, let's do, yeah, you guys screwed up the demo. Let's do the problem now. Let's see. Okay, so here's another problem we can work on. And this one's in 2D. And again, we're going to deal with phase and position. It's got old really fast. Just to give you more time, more practice. Okay? Let's see. So let's look at that and think about that a little bit while I do something here. I'll set up the next demo disaster here. Think about that. I'm not expecting you to do it in the little time I'm giving you. I'm just think about it for a second. Okay. Let's see. I'm just going to be drawing it, so don't worry. I'm just drawing it. All right, let's look at it together. You thought about it a little, what you might do. We've got two speakers, 1.5 meters apart on the y-axis, and then a listening device, which is an ear or something, I don't know. A listening device is 3 meters from the top speaker along the x-axis. So this is what I meant, okay? We'd try to write it nicer for an exam or something. We'd probably draw it for you. The listening device hears constructive interference, but the speakers are 180 degrees out of phase. Now, you might say if the speakers are out of phase, how could you ever get constructive interference? I mean, they're out of phase. Oh, but it's different distances, right? Different distances. You can have different phases and different distances, and things can end up in phase. Well, then you might say, it seems like, how could it happen? Well, it's only going to happen at certain wavelengths, right? So we got to figure out what are the wavelengths where this could possibly happen. That's the question. So first I would draw it and realize, oh, it's a right triangle, right? 1.5, 3. So R1 equals 3, doesn't it? Yes. This is R1 equals 3. What is R2? That's from here to here, Right, there's R1. R2, so first thing you need is get R2 from the geometry. It is the hypotenuse. All right, so R2 is the square root of 3 squared plus 1.5 squared. 1.5 squared plus 3 squared. So you do that and you get 3.35 meters. Okay. So at this point, it's actually exactly the same as a 1D problem where I said they're spaced by a difference of 0.35 meters. It's like if you put this back by 0.35 meters. It's really the same thing. We've done the 2D part pretty much at this point. Okay? But then there's that phase part. I know phase gives people not hemorrhoids. Phase gives people heartburn. That's what I was trying to say. Let's see. So is 180 degrees out of phase? What does that mean? So you could say, well, what I'll do is I'll say this one's phase constant is 0, and I just got to give this one a phase constant of what? Pi or negative pi? Pi or negative pi? That's the scary part, right? Because we could draw it real quick, and I could say, okay, here's 1 like this, right? And I could say, okay, 2, if I think of it as negative pi, that means I've pushed it forward by a half cycle, and it's really here. Right? So then they're out of phase, so that makes, the source is out of phase. But I could also say, what if it is, this is if it's negative pi. Negative pi pushes it this way. Well, so I've run out of room. What if it is positive pi? Right? Then that means you'd pull it back. You'd come back like this. Right? This is 2, and you'd go, like that. Again, it's also out of phase negative. And if we extend these, right, we see they're really the same thing. I mean, if you move this thing by positive pi or negative pi, you're just moving a sinusoid by half a cycle. So it doesn't matter. I mean, the difference between these two is 2 pi, right? This is shifted forward by pi. This is backwards by pi. The difference in them is 2 pi. 2 pi is the wavelength. You can't tell the difference. Okay? So what do you do in a problem? Doesn't matter. You'll get the right answer no matter what you do. We're going to show you. Okay? You could also say, in this problem also, my other existential dilemma here is delta r over 2 lambda, delta r over lambda times 2 pi. Say I'm going to go with positive, plus pi. And now, what are we trying to do? We're making it constructive. Do I put 0, 0, 2 pi, 4 pi, 6 pi? What do you do? Right? It's hard to know. So I'm just trying to show you that all these things are arbitrary, but we're going to show you this problem with a lot of practice is they'll all give you get a bunch of different answers, and you got to just start plugging them in and see if they make sense. Is kind of what I'm saying. Just like before I guessed the one that would make the speaker move back. If I'd have guessed the other one first, you'd have said, oh, the speaker moved forward. I guess I should use the other case, and I bet you that'll move the speaker back. And then you'll see, oh, part C was the forward. I did them out of order. See? So that's what we're going to do now. We're just going to guess. We're going to say, let's do pi, positive phase shift to move it forward. And I think that's all we need for this. Yeah. And let's I think we do 0 first. Okay? So we'll do a bunch of these. Here we go. Okay. And then you'll get a feel for it really doesn't matter. You get all the answers are correct. You'll just get different correct answers. Okay? So let's start. Say, who in here has bad luck when it comes to doing physics problems? Yeah. Say, everybody has their hand up again. What do you know? And let's make a guess first. And let's just see what happens. All right. Let's see. So let's guess this. Delta phi is 2 minus 1, R2 minus R1. What would that be? That would be 3.35 minus 3. Right? There's nothing arbitrary about that. We chose to subtract 2 from 1, or 1 from 2. 2 minus 1. Right? Over the wavelength. That's what we're looking for. Right? Times 2 pi. Plus the difference in phase. We said we're going to go with pi for the shifted one, number 2, minus 0 for the original one. Right, so that's a pi difference between the two. And let's go with 0. All right? For the constructive interference. Right? Constructive interference. All right, if we do that, let's solve that. That's 0.35 over lambda. The pi's go away. This is a 1, though. It comes here, becomes negative 1. When we divide the 2 under it, you get a negative 1/2. And you get lambda's negative 0.7 meters. Oh, that's a little weird. Can the wavelength be negative? Well, under the guise of reversibility of time, technically, no. The wavelength can't be negative. Let's not talk about the reversibility of time. Okay? So then you would just say, well, this is a bad guess. Right? Maybe I shouldn't have made that pi. Maybe I shouldn't have made that 0. But this seems a little weird. It wasn't that much algebra. I could probably afford to do it again. I've got 13 hours to work on this class this week. Surely I could run this again, right? So let's try it again. Let's try to stick in 2 pi. Delta phi equals 3.35 minus 3 over the lambda I'm looking for times 2 pi plus pi minus 0. All right, I think I'm going to stick with my pi here, okay? But I'm going to say equals 2 pi, like that. Okay, pi's go away. This 1 comes up here, tries to make it negative, but it says, no, I'm 2, you're just negative 1. And it becomes 1, right? Here. So it ends up being 0.35 over lambda equals 1/2. Ah. And what is lambda? 0.7 meters. Hey, that sounds better. That's actually positive. Right? So there's the answer. It needs to be, if wavelength is 0.7 meters, the difference in the distance that those two go will have just the right amount of phase shift. And it kind of makes sense if you think about it. The difference is 0.35 meters. And we're saying twice that would be a couple of waves, but then the pi over 2 gets involved. Okay, I can't do a mental picture. The 0.7 meters is one answer, right? So now let's say, but what was the question? The question was, I didn't print it. Wait. What are possible wavelengths? Right, it's plural. So let's see if there are more. Well, let's put in 4 pi, right? Delta phi equals 0.35 over lambda times 2 pi plus pi equals 4 pi, right? So we're just changing. This is constructive, this is constructive, this is constructive, right? So pi's go away. This 1 comes over here, turns that into a 3. Okay, and the 2 times that is 0.7. So you end up with a lambda is 0.7 meters over 3. 0.7 over 3 meters. So that's another wavelength that would fit. All right, a fundamental 0.7 meters, 0.7 meters over 3. Let's do 6 lambda. Delta phi equals 0.35 over lambda times 2 pi plus pi equals 6 pi. And you just get 0.7 over 5 meters. So you can see we're getting shorter and shorter wavelengths that work. Okay? So lambda equals 0.7 over 5 meters. So there's a bunch of answers, and you could probably generalize that in your head to be lambda equals 0.7 over 1, 3, 5, 7, 9, 11, 13, 15, 17, 19, 21. Okay? So that's all the wavelengths. Somebody asked, why can't it equal pi, 3 pi, 5 pi, etc.? That would be deconstructive interference. And I think the question said constructive. Let's see. That would be a read the question moment. Here's constructive interference. Right. So if the whole problem had said it here's destructive interference, then you would put pi, 3 pi, 5 pi. Okay? So you see, this is a case where it's okay to just say, I'm not sure which one of these I should use. Let me try this. That was kind of nonsense. Let me try 2 pi, 4 pi, 6 pi. If you have super interference intuition, you can predict which one to use. But we don't all have that. I don't have it, so just try different ones. Okay? Could you also use negative 2 pi? You're crazy. I'm not going to do that. There's people looking. Okay? You can do that on your own time. But yes. You'd probably get a negative number, though, so probably not. Okay. Let's see. Now, we're going to talk about one more thing. Oh, good. I have time to break my leg here. Beats. This is the last topic here for today. Beats. So that was 2D interference. As you saw, very similar to 1D. We've practiced a lot. What if you had something other than pi? We have so many pi's, I don't know what you mean. Let's see. You may mean the phase difference. Instead of where I kept adding pi minus 0, it could be 3 pi over 2 minus 0. And do the math. You know. Yeah, you could have any phase difference. I said pi because the problem said they're out of phase. So out of phase means they have a difference of a half wave of pi. Okay, beats. Let's talk real quick about beats. Beats is when you superpose, remember that's just what physicists say by add, two waves with slightly different wavelengths or frequencies, whatever, slash frequency. So every problem we've done in interference so far, same wavelength, same frequency. Right? So what would that look like? Let's see. Oh, it's creeping up on me here. Basically, you would say, well, the disturbance I'm looking at, 1 plus 2, d1 plus d2. Right? Be the sum of the two disturbances. We can go back to 1d now. We don't have to do 2d. So you would say, well, if we had two just general waves, we're not even being specific here, A sine, what would it be? K1x minus omega 1t plus phi naught 1. There's a wave. How about another one? Let's let it have the same amplitude. Why not? Plus A sine, but now a different wavelength and frequency. 2. Now note, before the 1 was here, we're talking about two sources with the source in a different place. We put a 1 there. We've never put a 1 here before. Right, this means this one has its own wavelength and frequency. This one has a different wavelength and frequency. Okay? What if you added... So now to deal with it, how do we deal with this mathematically? It's kind of hard. But if you need to add two sinusoids of different amplitude but the same frequency, then you just add the amplitudes. But here you can't add two sinusoids easily with different things under the phase. Right? That becomes a mess. So I have like 5 steps of trig here. It's not worth doing. I'm just going to give you the answer. Okay? You use the sum to product rule. Right? It's a trig identity. If you have a sum of like sine A plus sine B, that's equal to some product of sine A and cosine B. There's a bunch of different ways to write it. Okay? I'm going to show you graphically. But then, that was not on purpose. It's my imported Japanese chalk. Let me get some of this scrub chalk here. Let's see. So then you could use some identities to show this is actually equal to 2A times the sine. And I'm going to convert it to frequencies instead of omegas and k's, because people hate that. It's 2 pi frequency average t. We're getting rid of the kx part. We're saying, what would you hear if you're at x equals 0? Times the cosine of 2 pi times 1/2 of the frequency difference times t. Okay? This is what you get with a lot of assumptions. Okay, so the reason, so x, so this is what you would hear at x equals 0 if this were sound. Okay, that's how the x went away. And I just said, let's just assume the phase constants are 0. So that got it down to a function just of time. And then when you have this function of time plus this function of time, this trig identity turns it into a product of two sinusoids rather than a sum of two sinusoids. And it looks like that. And the things that go in here, it's really f1 plus f2 over 2, which happens to be the average frequency, and then f1 minus f2 over 2, which is half the difference frequency. Okay? So, I could just write trig identities and you would just have to believe me. So I figure, why spend minutes on it when we could let you hear this and see it more directly? Okay? So what would you get? I'm just going to leave that like that. What would you get if you plotted that? Let's see, what would it look like? Let's try to predict what it looks like. Say we have the individual waves are very high frequency. Well, let's see. Why even bother to... I have a drawing that's much better than my drawing here. Okay, let's look at this. Let's just look at the cartoon, because it's very hard to draw. You can draw it. There we go. So this idea is that it's the product of two sinusoids, the average sinusoid and the different sinusoid. Right? So here we go. Let's look at it carefully and get like a visual on this. Does the equation only work if the amplitudes are the same across both waves? We're only going to use it where the amplitude's the same. It works other ways. Here's your two waves. So this is really in time. This is what, if the speakers were coming, the sound was coming at you, this is what you would hear at x equals 0 in time. They are at different frequency, and you can tell, oh, I'm going to use my pointer. You can tell because, look, here, the dip down aligns with the dip down, right? Because there the dip is right over the opening part there. Dip, down, 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 down. Wait a minute. Now the dip down is aligned with the dip up. So here they're out of phase. Oh, no, how did that happen? Well, just sit back and relax because it's going to be over here. Now they're back in phase. Oh, now they're out of phase again. So they are slightly different frequency. Okay? Two ways, slightly different frequency. Let's superpose them. Ooh, look at that. Look how beautiful. You can see in some places, when they were in phase, they superpose, and they're in phase. So you can imagine this will be constructive interference, big amplitude. Other places, they go out of phase. And then this is going to give us 0. Right? So all we got to do is add those two and see what we see, and it makes that. Right? This is real math from MATLAB. This isn't just me bullshitting you here. Right? So this is where they were constructive, and then it goes down to destructive. And constructive and destructive. Constructive, destructive. So if you imagine, just think about it. Two waves, slightly different frequencies going past each other, or together. Some places they'll be together, some places they'll be apart. And this is what you get. Right? So let's listen to two sounds that are slightly out of phase here, or out of frequency here. So let's see, here we go. Oh, we want them close to each other. Somebody shout out the frequency they want to hear. Very good. Okay. Let's see. Here, let's listen to 224. That's my personal favorite. Let's see. They're both at 224. Okay? Now I'm going to make one of them 226. Okay, so you can definitely hear it going up and down, but we can also think about what's the rate of that. It's about 2 hertz, right? It's 2 hertz, but the difference is, you can't tell that's 2 hertz? I have like no rhythm at all, and I can tell that's 2 hertz. Okay, I assure you that you guys can tell it's 2 hertz. Like when I dance, people like call an ambulance and think I'm like having some sort of something going wrong. The difference is 2 hertz, and we're hearing 2 hertz, but the formula had a half on the difference, didn't it? The formula said a half of F difference, but we're hearing F difference. But the reason is you're hearing every beat. You're hearing 2 beats per cycle. So if you think about the cosine that's modulating this function, it looks like this. All right, so here's a complete cycle of the cosine. Starts here, ends here. Right, so we hear beat, beat, wah, wah. Right? So in the end, there's a factor of 2 in the cosine, in the trig identity, but there's also a factor of half in the trig identity, but there's a factor of 2 because you hear 2 beats per cycle. So those cancel out, and with beats, you always hear the difference. Right? So let me set the difference to 4. So this is 224, let's 228. There's 4. 1, 2, 3, 4. 1, 2, 3, 4. No, I won't. But if we get a big difference, then what do you get? Oh, yeah. The big difference is what we hear is like bad, out of tune, right? And then eventually it sounds nice. Oh, yeah. So when you like music, it's because you find the beats pleasing. But when you don't like music, and then you get this one, you start thinking about physics. Oh, shit. Oh, no. All right, okay. So now, I'm going to attempt a demo for you I've never done before, highly unadvised by my doctor, okay? Let's see, here we go. So there's another thing you can do with beats called velocimetry, okay? Doppler velocimetry. Let's combine the Doppler effect with beats. So if you remember from before, the Doppler effect is where when you have a moving source, it changes the frequency, right? So we don't have to rush this. I got a few. Let's just calm down. Let's just do this one and see what happens. I don't know. So this is the way this is used in a lot of technology, biomedical imaging, ultrasound, etc. So Doppler, and this is a very common topic on a certain exam that I am not going to mention, okay? Basically, you measure speed with reflection and Doppler shift. So what we're going to do, and we're not really going to do it by reflection, I'm just going to have two sources down here. Let me see if I can do this real fast here. Let me see. How much time do I really have here? Oh, 4 minutes. The thing itself only takes seconds. This is here. The speakers are coming down here with me. Here we go. Speakers come down here. Yes, speaker 1, speaker 2. They got to be free. Oh my God, they're tied in a knot. How did that happen? Oh, this is totally worth it. Totally worth it. Oh yeah, this is going to work like you're going to be writing checks to Rice when you're older. I remember when Hafner broke his neck doing that demo. It was the greatest thing I ever saw in my educational career. So what we're going to do is I'm going to be like the fast-moving object with the source. Okay, so we're going to have the frequency of this thing will be 800 hertz. So we're going to crank 800 hertz out of here. And I may have them in phase or out of phase. Yeah, let's see. There we go, in phase. Okay, and we're listening to it over here, right? So I'm going to start recording over here. There's a speaker in here. I only want to hear the sound direct. I don't want to hear it bouncing all over the place. So the speaker's in a box, right? And the frequency of the speakers, one is at 800 hertz. But the other one is going to be moving, and it's going to be what you learned last semester, F naught over 1 minus V over Vs. Vs, the source speed, over V. So 800 over 1 minus however fast I can go over 343. I can't go very fast compared to 343. So this is going to be like 800 and 802. This will be 800. This will only get up to 802. It's hard to hear the difference between 800 and 802, but it's easy to hear the beats, right? So all we got to do is record it and play it and see if we can hear the beats. All right, here we go. 2 minutes, plenty of time. Okay, here we go. I'll go as fast as I can. Oh, this needs to be over here a little bit. This needs to be there, like that. All right, you ready? All right, here we go. Okay, let's listen to it now. Let's listen to it and see if we can hear the beats. When I grabbed it and moved it, I was the moving object. Here we go. Here's me yelling. Okay, let's get it. Did you hear it right at the end? It went wah wah. That was it, right at the end. Whoa, whoa. Okay, so I'm going to make that into the homework problem.